Have you ever stopped to wonder, can a machine actually simulate the real world? Like, not just memorize a bunch of images or slap a label on a picture of a cat. I mean, fundamentally grasping the underlying physics, the rules, and the raw variations that make up our reality. Well, welcome to today's Explainer. We're going to unpack a major breakthrough that attempts to do exactly that. We are demystifying variational autoencoders, or VAEs. Honestly, it's one of the absolute most elegant architectures in modern AI. Let's get into it.
And hey, don't sweat it if deep learning papers usually read like an alien language to you. We've got a really clear roadmap today. We'll start with the generative modeling quest, hit the intractability roadblock, and then enter variational autoencoders. From there, we'll break down the evidence lower bound, the famous reparameterization trick, and finally wrap it all up in the conclusion.
All right, part 1, the generative modeling quest.
So before we look at how a machine learns, we really need to nail down what it's actually trying to learn. Usually we think of discriminative modeling, right? You hand an algorithm a picture and it confidently says, yep, that's a dog. It's just learning a direct map from an observation to a label. Generative modeling, though, that is a much more ambitious game. It's trying to learn a joint distribution to literally simulate how data is generated out there in the real world. Think about a meteorologist. They don't just look up at a cloudy sky and guess rain. No, they use complex equations to map out the actual underlying physics of the weather. Generative models are trying to do the exact same thing. They want to unveil the generating process by mapping out the causal relations of the world. Because think about it. Once you understand the generative process of, say, an earthquake, you can apply that knowledge anywhere. You aren't just limited to the specific place you trained your model. To really ground this abstract math in physical reality, just look at this tiger cub. If we want a machine to generate this specific image entirely from scratch, it has to understand multiple layers of reality. It has to implicitly get the concept of a tiger. Imagine it existing in a 3D space, position it perfectly peeking out from behind a tree, and then project all of that insanely complex geometry and lighting onto a flat, high-dimensional pixel grid. That's a massive sequence of causal events that the machine basically has to reverse engineer and simulate.
Which brings us to part 2, the intractability roadblock. Here's the thing. When researchers first tried building models to uncover these hidden causes, they hit a massive brick wall. It comes down to this concept called intractability. Basically, to train these models, you have to calculate the probability of the data under your model. To do that perfectly, you'd literally have to consider every single possible combination of hidden variables that could have resulted in the data. And for high-dimensional data, like images, well, you end up with an integral that just lacks an analytic solution. There's no neat little formula. The exact probabilities are literally too complex to compute. We're talking taking more time than the universe has existed. And here's the kicker. If you can't compute the probability, you can't calculate the gradients. And if you can't calculate gradients, your neural network absolutely cannot learn. The whole thing just halts.
So what happens next? Part 3. Enter variational autoencoders.
How do you bypass a math problem that's essentially impossible to solve? Well, you use an approximation. The sheer genius of the VAE is that it splits the problem into two cooperating neural networks. Step 1 is the encoder, which we also call the recognition model. When you feed it an image, it doesn't give you one single absolute answer about the hidden variables. Instead, it outputs a probability distribution. It's basically making a really highly educated guess about the latent factors that might have created that image. Then, step 2 is the decoder, or the generative model. It takes a sample from those guessed hidden variables and tries to reconstruct the original image from scratch.
As the original authors perfectly summarized here, the recognition model is the approximate inverse of the generative model, according to Bayes' rule. They're constantly supporting each other. But the truly revolutionary part here is that this recognition model uses a single set of neural network parameters for all the data points. This is a process known as amortized inference. So instead of running some massively expensive, slow optimization loop for every single new image you show it, the encoder learns a general function. It essentially amortizes, or spreads out, the cost of inference across the entire dataset. That allows it to evaluate totally new data in just a single lightning-fast feed-forward pass.
Moving on to part 4, the evidence lower bound.
Okay, so we've got these two networks working together, but how do we actually grade them? We use something called the evidence lower bound, or ELBO. Remember earlier when we established that calculating the exact true probability is completely intractable? Well, we just don't try to calculate it perfectly. Instead, we calculate a lower bound on that probability. By optimizing this ELBO, we're safely pushing up the actual log likelihood of the data. And the most beautiful part of this, the ELBO is incredibly mathematically cooperative. It actually allows for the joint optimization of all parameters in both the encoder and the decoder, all using standard stochastic gradient descent.
You can really just think of the ELBO as this brilliant 2-for-1 deal for the neural network. Every single time the algorithm takes a step to maximize the ELBO, it's doing two crucial things at once. First, it approximately maximizes the marginal likelihood. That means it's reducing the reconstruction error, basically making the generative decoder way better at recreating realistic data. And second, it minimizes what's called the KL divergence. To put that in plain English, it forces the encoder's educated guesses to get closer and closer to the actual true hidden distributions. So you get a better generator and a better recognizer all in one single mathematical stroke. It's pretty amazing.
Let's look at part 5, the reparametrization trick.
Now, there is a catch here, and solving it led to arguably the most famous contribution of the VAE paper. We hit another severe structural roadblock. Remember how we said the encoder outputs a probability distribution, and then we have to take a random sample from it to feed to the decoder? Well, taking a random sample naturally induces sampling noise. In a neural network, learning happens through backpropagation, right? Calculating the chain of derivatives backward through the network to update the weights. But here's the problem. You literally cannot directly backpropagate gradients through a random variable. The randomness totally blocks the path. The gradient vanishes and boom, learning stops again. You can really see the problem and the solution perfectly right here. Look at the original form on the left. That Z node is blue, which represents a random sampling process sitting right smack in the middle of our network. The backpropagation tries to flow through it and just dies. But now, check out the reparametrized form on the right. Notice how the random node has been pushed out to the side. It's now this external noise variable called epsilon. The Z node is gray, meaning it's a completely deterministic operation now. It's just the network's output plus that external noise. The path for the backpropagation is now completely clear. I actually want to read a quote directly from the source material here because it really hits the nail on the head. We can externalize the randomness in Z by reparameterizing the variable as a deterministic and differentiable function. It's such a ridiculously elegant workaround. By just slightly rewriting how the sample is drawn, you pull the randomness from an external standard distribution and then scale it by the network's parameters, the neural network can suddenly backpropagate right through what used to be a solid wall of random noise. Suddenly, the entire VAE architecture clicks into place and becomes end-to-end trainable.
Finally, part 6, conclusion. Now, to give you the full, balanced picture here, we do need to highlight a couple of known limitations with VAEs. First up are optimization traps. Early on in training, the reconstruction loss might be pretty weak, and the network sometimes finds an easy, lazy way out by just ignoring the hidden latent variables entirely. So researchers actually often have to use a sort of warm-up schedule. They slowly introduce the KL divergence penalty so the model doesn't just get stuck. The second limitation is blurriness. Because VAEs are optimized over the entire distribution and get strictly penalized if they miss anything, they tend to generate safer, more dispersed, and kind of slightly blurry samples, especially when you compare them to the razor-sharp, even if slightly more fragile outputs you'd get from something like a generative adversarial network or a GAN.
So we've covered a ton of ground in this explainer today, from intractability to amortized inference, right down to the reparameterization trick. But beyond all the intense math, VAEs represent something truly profound. As the researchers themselves note, by using the auxiliary task of predicting the world to force the creation of meaningful representations, we are literally building a model of reality. And it leaves us with this incredible, provocative question, drawn directly from the core philosophy of the text. By forcing machines to predict the world, do we teach them to fundamentally understand it? It's definitely something to chew on the next time you see AI generate an entirely new image out of thin air. Thanks for joining me today. Keep questioning, keep learning, and I'll catch you next time.